Welcome back. So, we were discussing the variational methods the last class, specifically the latent variable models, the variational autoencoders. Quickly run through the basics of VAE, the formulation before we move on to the implementation of VAE in terms of neural models. If you recall, we defined latent variable models. The setting is exactly the same, that we have n data samples that are sampled IID from an unknown distribution, and these are random variables in d-dimensional Euclidean space. We define the latent variable model as all those class of models where there is an extra hidden variable that is introduced. The model is defined as the marginal over the joint distribution between the latent variable and the data variable, integral p theta x comma z, where z is the latent variable. It is in some dimensions k, and typically the number of dimensions, number of variables in the latent space is much less than that of the data space. K is much less than d. This is only a typical choice. The model does not demand that it should be less than k, less than d. Now, the problem is that of minimizing the KL divergence. Find the model parameters theta such that the KL divergence is minimized. And we saw the equivalence between minimizing the KL divergence and maximizing the expected log likelihood of the model under the data distribution. So, expected log p theta x, where the expectation is with respect to px, is what we optimize. Now, this problem is intractable under the latent variable models because we do not know what the latent variables are. So, we formulated an alternate problem using a lower bound that we constructed on the log likelihood of the data. Okay. And we invoked the Jensen's inequality to construct the log likelihood, and we call that lower bound on the log likelihood as the evidence lower bound, or elbow, okay, that has this particular form, where Q is the variational latent posterior, which is a distribution on the latent variable conditioned on the data variable, right, Q of z given x. Now, in any latent variable model which is optimizing for the lower bound on the log likelihood, the objective is of two folds. One, we need to maximize the evidence lower bound with respect to the model parameters theta, and simultaneously we need to find the variational, the optimal variational latent posterior, right. Now, we saw that in the cases where the posterior of the latent variable given data with respect to model is tractable, then the optimal latent posterior would be Q, optimal latent posterior would be that particular distribution p theta of z given x, as in the case of a mixture density. Now, the question that we will be asking now is that if there is a case where the distribution of the latent variable given data is not tractable, how do you construct latent variable models, right. Now, I mean that is where we come up with the neural latent variable models, of which VAE and DDPMs are special cases, diffusion models are special cases. The goal of any neural latent variable model is that we first have to learn a latent variable model with an unknown posterior p theta z given x. Okay. Now, there is this Q of z given x, right, which is the variation latent posterior, and p theta of z given x, just to ensure that the symbols are correct. So, what is p theta of z given x? See, a theta will give you a model. Okay. Now, once a latent variable model is constructed, there is a posterior of the latent variable given the data variable under the model distribution, that is p theta of z given x. Okay. So, remember what it was in the case of a mixture density, right. We used the Bayesian law to actually find this out, p theta of x given z times p theta of z divided by the normalization factor. Now, not knowing p theta of z given x actually amounts to not knowing p theta of x given z, isn't it? Because if you know one, you can know the other using Bayes' law. So, if you do not know the conditional distribution of data given the latent variable, then this is not known. In those cases, how do you construct a latent variable model is one question. The other objective of a latent variable model is, of course, we need to sample from p theta of x given z, because that is our generative part. Now, this is a generative model that we are looking at. The third thing is that it has to enable posterior inference, which is that you compute or estimate Q of z given x, which is not p theta of z given x. Now, you have to estimate Q of z given x, because that is your posterior inference, whatever embedding, extraction or clustering, whatever it is. Any latent variable model has to ensure that this distribution can be computed or estimated. So, these are the three goals that we would have when we construct any neural latent variable model. Okay, so we will look at algorithm for a neural latent variable model, specifically look at the variational autoencoder. That's what the model is called. And yeah, so we start with the elbow, and last class I had broken down this elbow into two terms using the definition of the joint distributions. Joint distribution is defined as product of the conditional times the marginal. Now, if you do that, the second term that you get here, which is an expectation of log of q divided by p theta of z with respect to q, is the definition of the KL divergence, right. Now, the elbow that we would want to optimize will have two terms, this boxed item. The first thing is an expectation of the log of p theta of x given z with respect to the variational posterior minus the KL divergence between the variational posterior and p theta of z. Now, this equation is sort of very sacrosanct, because this is the equation that every model in the family of VAE optimizes, every model in the family of diffusion model optimizes. Okay. So, it is basically the lower bound that we have constructed on the log likelihood written in terms of the conditional data likelihood and the KL divergence between these two distributions, that is it. Okay. Fine. Now, I stopped the last class by telling you that the whole idea in all neural latent variable models is to represent the constituent distributions that appear in elbow in using neural networks. Remember the last class I asked you this question, what do you mean by representing a distribution using a neural network? The entire field of so called deep learning is doing this, that it represents distributions using neural networks. And what do you mean by representing distributions using neural networks? I said there are two ways to do this. This is not any textbook or standard term, this is my way of saying it. So, one I call the deterministic representation, where neural networks give you samples from the distribution that it is trying to optimize, that is trying to represent. Examples are the sampler in a GAN. The so called generator network in a GAN is not explicitly giving you the distribution function, or rather it is giving you samples from the distribution that it is trying to represent, which is in that case it is p theta of x, right. And the classical classifier in the discriminative machine learning can also be seen as a sampler from the distribution p of y given x, isn't it. So, it is not giving you the distribution, it is giving you a sample from the distribution, correct. Now, there is another representation which is called the probabilistic, so called probabilistic representation, where neural network will not give you the sample from the distribution that it is representing, but it will give you the parameters of the distribution that it is representing. Now, the difference between these two representations is that in the deterministic representation, you need not assume a functional form on the distribution that you are trying to estimate. But in the probabilistic way of representing things, you will have to a priori assume a distributional functional form of the distribution that you are representing, because neural network will only give you the parameters of the distribution that it is trying to estimate. Does that make sense? Okay. Now, in the variational autoencoder's case, we use probabilistic representation of neural networks, where we use neural networks to get the parameters of the distribution that we are trying to represent. Okay. Okay, fine. Now, let us construct the algorithm of the variational autoencoder. Now, this is the objective that we are that we want to optimize, and we have I told you that we represent both the distributions that come up in the objective function using neural networks. Now, there are two neural networks, one is representing the variational posterior q, the other is representing the conditional data likelihood p theta of x given z. Okay. These are the two neural networks. The first one takes x, and by the way, I mean this should be obvious for you people who have studied probability theory. See, when we write conditional distributions, when we look at conditional distributions q of z given x, okay, this actually means that the conditioned random variable is fixed to a particular value. I hope that all of you know this. So, this seems obvious, but lot of people do not appreciate this. The moment you write conditional distributions, the conditioned random variable is fixed to a particular value. It's not a random variable. We are talking about a distribution where the condition random variable is fixed to a particular value. I mean, for brevity we don't write this, but whenever we write the conditional distribution, we always mean that the condition random variable is fixed to a particular value. Why am I saying this is because we are using neural networks to represent conditional distributions, which means that the condition random variable is fixed to a particular value. That becomes the input to the neural network. Now this x that goes as an input to this neural network is actually the value that this condition random variable is taking. Okay. So now we have a neural network that is representing the distribution q of c given x in a probabilistic manner, in the sense that it outputs the parameters of q phi of z given x, okay, takes x, which is one realization of the random variable x, as input. Okay. So let us represent the parameters of this neural network using phi and call this the encoder neural network. I will tell you why it is called encoder neural network. I think it is for obvious reasons, right. It's giving you the distribution of q of c given x. Okay, that is one neural network. There is another neural network which is again representing the conditional distribution p theta of x given z. It takes z as an input, okay, and gives you the parameters of p theta of x given z. Please note that these two neural networks are not connected, like in the sense that there is no chain that connects these two neural networks, right. They are independent neural networks representing these two distributions for now. Is that okay? I told you about the predictability of human beings, right. So there is no direct connection between encoder and decoder, is something that I have written. I mean, I didn't see that while I said this, but yeah, unfortunately human beings are too predictable. Okay, so phi and theta denotes the weights of these two neural networks respectively, and of course once we have a neural network and an objective function, we know what to do next. We just invoke our holy gradient descent algorithm, first order gradient descent, and just train the neural networks or learn the parameters which would optimize it. Now the rest of the discussion in this class is now on how to find the gradient of this particular objective function with respect to the encoder and decoder parameters, because that is what we need to for gradient descent to work. That is it. Okay. Right. So now let us consider, actually there are 4 terms that we have to look at now. Gradient is a linear operator, so you can push the gradient inside 2 terms that are there. See here, this is the objective function that we are trying to optimize, and we have 2 terms here with an additive addition operation here, and gradient is linear. So I can push the gradient here, right, which means that I have 4 terms that are to be computed. The gradient of the first term in elbow with respect to the encoder parameters, and the gradient of the first term with respect to decoder parameters, and the other 2. So we look at computing all 4 terms one after the other. Okay. So it's not trivial, I'll tell you for a particular reason. Some terms are trivial, some terms are not. We will look at the non-trivial terms first, and then we'll go to the trivial terms. The first thing that we have to do is that we need to compute the gradients of the elbow with respect to the encoder parameters phi. Okay. How do we do that is the question. So it is not trivial. So why is it not trivial is for the following reason. Now look at this expression. We want to get the gradient of an expectation, okay, of some function, and this expectation is with respect to a distribution. Now this distribution is parameterized by the same set of parameters with respect to which we are seeking the gradient. Got it? Now this is a problem. So if you have looked at the popular literature of what blogs etc., where VAEs are described, they would say that you cannot back propagate through a sampling operation, is what people say. What does it even mean? Where is the sampling? Where is the sampling that's happening? I mean, one way to look at it is that the z that you are getting here, which is the condition random variable, is getting sampled from the same distribution with respect to which you are seeking the expectation, and that distribution is also parameterized by the same set of parameters with respect to which we are seeking the gradient. Now why is this even a problem is not convincing enough, right? So I just wrote up a few equations here to ensure, to ensure that it will come up algebraically very nicely. Okay, let's look at that. Now the above term that we are trying to compute is very similar to this, right? So we have the expectation of a function, and the expectation is with respect to a distribution which is parameterized by the same set of parameters with respect to which we are seeking the gradient. Okay. So, I do not have to write this, right, I mean just mapping what distributions are and all that. Okay. This is what we are looking at. Now, let us expand this expectation, assuming that that P is a continuous distribution, that you write the gradient within an integral. The expectation is integral P psi V times F psi V dV, right, and the integral is with respect to V. Now, integral is a linear operator, you can always push the gradient inside, push it inside, and once you have the gradient inside, you have two functions of psi, invoke the product rule, right. So, what does the product rule of calculus tell you? That if you have two functions and you want the gradient of it, just write the gradient of the first function times the second plus the integral the gradient of the second function times the first. That's what the product rule tells you. Now, the first term, look at this first term. What is this first term? First term is the expectation of gradient of this function with respect to p psi. We know how to compute it, because the moment we have expectations, we can invoke our law of large numbers and use sample estimates to do that. What is the second term? The second term is not an expectation, because we have the product of a function with the gradient of a density function. Okay. Now, this cannot be computed unless you know the density function and the gradient of it. Now, the whole problem that we have is that we do not know the density functions, one. The second thing is this integral is also not tractable, because the variables that we are looking at here are coming from very high dimensions. One, this integral is not tractable. The second thing is that we do not know the density function, therefore, the second term, which cannot be written as an expectation, cannot be computed. Now, this is the problem. Okay. So, which means that the gradient of the expected value of the log of the conditional data likelihood with respect to the variational posterior cannot be computed. So, how do you train that neural network is the question. Do you appreciate the problem well? Because this is why, I mean, this is the problem that the original authors of VAE paper look at. See, this has nothing to do with the particular functional form that it takes, etc. Wherever you see, this is a general idea. Wherever you see this kind of a computational form where you need to find the gradient of an expectation of a function with respect to a distribution, and that distribution itself is parameterized by the same set of parameters with respect to which you are seeking gradients, you will end up having this problem. So, that is why the solution that we will be looking at right now, which is called the reparameterization idea, is general enough to be applied to any scenario where you see this kind of a problem. Okay, it is not restricted to only the VAEs. Wherever you see this sort of a mathematical issue, the reparameterization trick can be applied. Can somebody think of a solution to this problem? Of course, if you know what reparameterization is, then you know the solution. But yeah, so look at this. Is there a way to solve this problem now? Any suggestions? See, for one, all that we need to do is that we need to get the dependence of this distribution, get the dependence of this distribution on C out, that is it, sorry, phi. Here, if you somehow represent this distribution in terms of something else that does not depend on phi, then we are done. That is all we need to do. So, that's reparameterization. Can we do that is the question. Turns out we can. So, let us look at what the idea is. This is precisely what I said. Now, this is what we have. We have the gradient of an expectation of a function with respect to a density, and that density is parameterized by some set of parameters that we cannot, that we do not know how to compute. Now, all we have to do is that if we can represent this random variable, okay, whose distribution that we are computing, in terms of another random variable which is independent of the parameters, and write the expectation with respect to that, then we are done. We have been doing this sort of reparameterization like multiple times in our probability theory courses. Let us see what that is. Suppose there exists another auxiliary random variable, call it epsilon, coming from a distribution P epsilon. Now, P epsilon is not dependent on psi, which is the parameter with respect to which we are seeking the gradient. Now, let us say that I can express the random variable V in terms of a function of this auxiliary random variable epsilon. Suppose that sort of a random variable exists, then the expectation that I am computing, expectation of this function with respect to p psi, can be now written as an expectation of f psi of g of epsilon, because v is g of epsilon, and this expectation will now be with respect to p epsilon, not p psi. So, this is called the law of the unconscious statistician. Please prove this. All I am saying is that if there exists a function of a random variable, you can write the expectation of the function of one random variable in terms of the function expectation of the distribution over the other random variable. You just have to expand this expectation and use the inverse of this function to write this. It's a trivial result. Please show that. Okay. Now, if we do this, then what happened is that the dependence of this expectation on psi is gone, right. Now, the gradient of this expectation with respect to p psi now will be the gradient of this expectation with respect to p epsilon, and now this can be now written as sample averages using law of large numbers, where now the samples are coming from p epsilon, not from p psi. That is it. That is all about reparameterization. What is the idea? The idea is that represent one random variable using some other random variable, and the distribution of the other random variable now is independent of the variable with respect to which you are seeking the gradient, correct. And the expectation is, the original expectation is now represented in terms of an expectation over the distribution of the other auxiliary random variable. That is the idea. Okay. Now, can we do this is the question. Okay. Turns out we can. We have actually seen multiple ways of doing it. So, let us look at one of the ways that the original VAE paper suggests. This is not the only way to do it. It is one of the ways of doing it. Let us say that our distribution q psi of q phi of z given x is Gaussian. Okay. And I have explained this notation to you, right. Whenever I write distributions, this is the random variable, and whatever comes after the semicolon are the parameters of it. Okay. Now, please note my notations carefully. Now, I am saying that this is a Gaussian distribution on random variable z, having the parameters mu phi of x and sigma phi of x. Why? This phi represents that this distribution is the outcome of this neural network. Okay. And an argument x tells you that it is a conditional distribution whose condition random variable has this value x that goes as an input to the neural network. That is why it is mu phi of x. Makes sense, right? The parameters of this distribution is the output of the neural network with parameters phi. That is what I am trying to say. Okay. Let us say that it is a Gaussian distribution with mean mu phi and variance sigma phi. Now, how is it done in practice is that you take a neural network which takes x as an input, data point as an input, and this neural network will output mu phi and sigma phi as outputs. That is it. Correct. It will be a function of phi. Yeah, that's a good observation, because it has to go somewhere, right. So, that it is pushed to that g, that's how it is done. Okay. So, typically when you implement, I will talk about it, typically when you implement, what is done is that if the, let us say that my random variable z is in k dimensions, then the number of nodes in the last layer of this neural network will be k plus k squared. Why? K is for mean and k squared is for variance. If you want to simplify this, assume that the variance of this distribution is diagonal and make it k plus k. That is one assumption that you can make, but in general it can be k plus k squared. You see why it is k plus k squared, right? Yeah, that is how you implement it. Now, we have to reparameterize. This is a standard result. Any Gaussian distribution can be reparameterized using the normal distribution. Why? All you need is an affine transformation. You take the normal distribution and make it undergo an affine transformation, which is a scale and a shift. The moment you do that, the new random variable will be Gaussian with the mean given by the shift and the variance given by the scale. That is one way to reparameterize. right. So now this auxiliary distribution, right, is independent of the parameters. Now as he rightly pointed out, the g function, which is the scale and shift, now is a function of phi. That is what you said, na? That should now it is a function of psi, because of course I mean that has to be deliberated to some other way, that is how it is. This is one way to do it. The other way to do it is this so called inverse CDF method. Do you know this? I think you have done it in your probability theory course without realizing what it is. See, here is a nice result from probability theory. Now we know that functions of random variables are random variables, correct? Now distribution function is a function on random variable, correct? So now distribution function itself is a random variable. You take a random variable, construct its distribution function, which is also called the CDF. Now distribution function itself is a random variable, right? And do you know what would be the distribution of the distribution function? Always uniform. So this is a standard result. Now you can prove, actually take it as a homework and do it. Take any random variable, take its distribution function. Now treat it as another random variable and find what the distribution function of the distribution function as a random variable is, and it turns out to be uniform. Okay. Now we can use this result to reparameterize. How? Now suppose z is a random variable and fz of z denotes as CDF. Okay. Now we know that the distribution of fz of z as a random variable is uniform, and it is uniform between 0 and 1, because the support of the distribution function is 0 1, no? The range of the distribution function is always 0 and 1, and therefore the support of the distribution function will be 0 and 1. Okay. Now if you take that as a random variable, then we know that it is always uniform. So which means that if you take a uniform random variable between 0 and 1, it is always the distribution function of another distribution function, okay, which can be recovered by taking the inverse of the distribution function. So if you take a uniform random variable and make it pass through the inverse of a CDF of any distribution, then the resultant random variable will have the PDF of the random variable whose distribution function that this inverse correspond to. Does it make sense? Maybe too many times I said distribution functions, but yeah, that is what it is. This is called the inverse CDF method, which means that you can convert uniform random variable to any random variable, so long you know what the inverse of the random variable or the distribution function of the random variable that you want to recover. In fact, this is how we know how to sample from a Gaussian distribution. I think there is a name for it, I forget. So Euler box, some transformation, right? It's box Miller transformation, right? Yeah, that's the inverse of it. So which converts a uniform random variable to a Gaussian random variable. That's how we have this random function, right? So all the pseudo random number generators sample from uniform distribution. Okay. See, one of the favorite interview questions that people ask in so called data science interviews is that I am giving you a let us say a coin. I mean, they will not say distribution, etc. There's a die, okay, which has some m faces, and all of them have some probability p1 to pm. Now they will ask you to write a function that can sample from this, that will sample in accordance to this. The solution for this is inverse CDF method, that you assume that you can sample uniformly between uniformly from discrete uniform distributions, and compute the inverse CDF, which is a deterministic function, and you get a sample from the uniform distribution, pass it through the inverse of the die, the distribution that is giving you that m phase die, and that will make it samples from that distribution. Okay. Turns out that you can use I mean this computing the inverse of a generalized discrete distribution is an O(n) squared computation, and you can bring it to log n by having some incorporating some algorithmic tricks. Okay, that's why they ask you that question, right? You have to make it optimized. Anyway, so this is the inverse CDF method. Is another way to reparameterize, which means that you can reparameterize any distribution using a uniform distribution using the inverse CDF method, provided that you know how to compute the inverse of the CDF. Okay, fine. Questions so far? Yeah. Yeah, the question is how do we use inverse CDF method here in the context of neural networks, right? You only choose those distributions, you parameterize your Q using only those distributions for which you can compute the inverse CDF, that is it. See, for instance, if you want to make it let us say a generalized discrete distribution, then the inverse CDF is known. Your models are restricted to having those set of parameters, those set of distribution functions for which you know the inverse CDF, or else either you use those distributions for which you know you can compute the inverse CDF, or you take those distributions for which you can reparameterize, that is it. If you cannot reparameterize, you can't solve this problem. People have tried ways to solve this problem, which is use a vector quantization, etc. I will come to that in a while in the class. But at least in this formulation, you have to look at only those distributions for which you can reparameterize. That is a known limitation of this formulation. Okay. Anything else? Yeah. We are not going with that assumption. This is one of the instantiations of it. See, if you take it to be Gaussian distribution, not normal, it is a Gaussian distribution. If you take it to be a Gaussian distribution, then you can reparameterize this way. You can take it some other distribution and reparameterize in a different way, that is it. In fact, there are variations of VAEs where people have taken Q of Z given X to be a mixture density, and then you reparameterize. The only thing is that you have to ensure that this expectation can be computed, so that you can backpropagate and do a gradient descent, because finally you need to optimize elbow. As long as you can come up with a choice on Q phi of Z given X, which can solve this problem of computing the gradient, it is fine, any choice is fine. This is one of the choices that is made, so that you can understand what is happening, that is it. Yeah, we are not, it is not a model of, it is not a methodological assumption, it is just one instantiational assumption, that is it. So you take this instant and this is how it turns out to be in that particular case. Okay, so that is it for today. Thank you.